trying to give as much verisimilitude as possible. So people can say hi to each other. You can say where you're from. You can say how you know me. You can say what your background is on math, what you expect to get out of the talk. And that's only going to be for about a minute. So just like you're sitting down, talking to the person to your left and your right. And then I will bring us back and we will begin the talk. Now, do we have all my committee here? I think we're still waiting on Dr. Zhuang. Is that right?
But I see the enhanced snacks. I think.
Oh, is that
hiding
young?
behind there?
Okay. So it is 3 o'clock. I'm going to send us into breakout rooms. If you weren't here a second ago, that is just going to be to simulate what you might have in an actual meeting. You can get to know people. You can talk about where you're from, who you are, how you know me, and I'll bring you back. So here goes. So I'm going to more in breakout rooms. Yes, okay. So I'm going to do 2 to 3 participants per room. You're sitting someone on your left and your right. Okay, here we go.
Michael's got this down to a science. One person on the left and one on the right. Down on the bottom left, there should be a place where you can click to unmute yourself.
Yes, I think I'm connected to audio. Can you hear me?
You're good,
Colin.
yeah. Oh, there you go.
Colin.
Colin, hi Colin, it's Vicki and John Robertson.
Oh, hi, it's so good to see you guys.
Good to
Hi,
see you.
Colin.
And hi Heather, we're Michael's mom and dad.
Oh, very nice to meet you.
Nice to meet you too. How does he know you?
He's taking my graph theory course right now.
Oh
Okay.
my God.
He did say he likes his teachers this semester, so he put in a good word.
That's good. I've enjoyed having him. I've had him in a couple of courses, and then
Wow.
I'm a reader on his thesis. So
Oh, wow.
through the whole process.
Oh my
Wow.
gosh, you are a reader, so you're going to be one of the few who understands this. Not gonna
I
be-
tried.
oh, what a.
He's got a few Easter eggs in his thesis, though. It's kind of fun.
What does that
Oh,
mean?
good.
Like surprises?
Yeah, there was like a big part of all these calculations he had to do. And he said, and now I've proved this, the Riemann hypothesis, this massive.
No, we saw that joke.
Yep.
Okay.
There was one I didn't catch. He had to point it out to me about a certain sequence of numbers. But
All right.
really fun. So I'm looking
Very
forward-
nice to meet you. Thank you for your help.
I'm so glad y'all could all come.
Yeah.
Yeah.
Us too. All right.
I
And
guess-
Colin, how you
Good to
doing?
see you, Mr. Robbins.
Good
I'm
to-
good. I'm good.
Yeah,
Yeah,
we were
good to see you guys.
disappointed. We were disappointed not to go to Michael's the regional competitions this year. It would have been this weekend.
The ultimate frisbee.
Oh, what has it been? Yeah, I played ultimate frisbee with Michael a couple years ago for
know.
context, Heather.
Yeah, that's why we're
Fun.
addressing that with you. We're letting you know.
Yeah, I know that's really disappointing. That would have been, I'm sure it would have been a blast, but
Yeah, yeah. Well, he was working on his thesis, so maybe better.
I suppose so. I'm excited to see
From what I hear, he needed the extra time.
it.
All right,
He's
we're
got
gonna
like
close.
60 pages, I think. It's a lot.
As people filter back in, please stay muted. Yep, but
Hey,
feel free to keep your video on and take some enhanced snacks from Enhanced Snacks. It just gives a sense of community. There should also be a thesis handout file that I would encourage you to download. I've sent it out to the professor before, but it gives some useful definitions that I'll be referring back to throughout the talk. So let me see. I think everyone
Can you
is back.
resend that file? I don't think it came through.
Don't think it came. Okay. Thesis handout.
It's in the top of the chat.
I think it only comes, I think it's only available to you if you came back before I sent it. So if you come back after I send it, you cannot see it.
Hmm.
And to resend it, I actually have to rename it. So this will be thesis handout 2. Okay, and now that you have that, we're off. So one of the reasons I decided to do that small exercise is that community is important. I'm gonna read a quote here. One of the marvelous things about community is that, sorry, I forgot to share my screen. So you should be seeing my screen now, which has a welcome slide and a quote.
Da,
Yes?
da.
Great. Wonderful, in the Russian spirit. One of the marvelous things about community is that it enables us to welcome and help people in a way we couldn't as individuals. When we pull our strength and share the work and responsibility, we can welcome many people, even those in deep distress. So my presentation is on restricted numerical ranges of digraph Laplacians, and our story begins in a Soviet satellite state, Czechoslovakia, in the 1970s, hence my flag. And I'm going to give some brief mathematical background. So the title of my presentation is Restricted Numerical Range of Digraph Laplacians. So I'm going to first define the Laplacian matrix, which is a matrix representation of a digraph or a directed graph. And this is also on your handout, so feel free to look back to it since I'll be going through it fairly quickly. So for a graph on n vertices, the adjacency matrix has a 1 in the ij position if vertices I and j are adjacent, and a 0 otherwise. The Laplacian is the diagonal matrix, which has the degree or out degree in the directed case of every vertex on the diagonal, and the Laplacian is equal to the diagonal matrix minus the adjacency matrix, or shortening our notation, D minus GA. And we will be taking Laplacians of digraphs or directed graphs for the most part. So that is the digraph half of my title. The numerical range half of my title can be explained as follows. For an n by n matrix acting over vectors in Cn, the numerical range of a matrix A is a convex set in the complex plane that can be described by this equation. That can be viewed as the conjugate transpose of X with its image under the matrix A, or sort of the image of A on the n ball, because we require our vectors to be of unit length. And so, since that was a little heavy, I'm going to give an example. So we have a graph here. Note this is a undirected graph. It does not have direction to its edges. The adjacency matrix is going to look like this. For a undirected graph, the adjacency matrix will always be symmetric because 1 can't be adjacent to 2 without 2 being adjacent to 1. And the Laplacian is equal to the diagonal matrix minus the adjacency matrix. So in this example, we see that the 1 vertex has 2 edges, the 2 vertex has 3 edges. In fact, this is the cycle on 4 vertices. Every vertex is going to have 2 edges, so we are going to have 2's along the diagonal of our Laplacian. And we have a -1 corresponding to every 1 in our adjacency matrix. So this is a good way to encapsulate the work of my thesis. I'm working with objects in one field of mathematics, graphs, and I'm visualizing them in a representation from another field, linear algebra, matrices. And we're actually sort of taking a third, I suppose, transformation of space where we're looking at these matrices or images of these matrices, which are related to the graphs in the complex plane by looking at the numerical range of them. So now some historical background that might explain my virtual background. We begin with our beloved Miroslav Fiedler, who may be known to some of you. He was a Czechoslovakian mathematician who defined the algebraic connectivity for undirected graphs as alpha in a 1973 paper. And later, his country experienced a peaceful Velvet Revolution against Soviet control. And so to symbolize that, I will now be changing my virtual background to a velvet. And one of the neat things about the Velvet Revolution is that people rallied by jingling keys, which was symbolic of opening doors. So anytime there's a result that you really like, if you happen to have a pair of jingly keys on you, you can just unmute briefly by pressing the space bar and then do that. But back to the history. The definition of alpha that Fiedler came up with is the second smallest eigenvalue of the Laplacian matrix for a graph. So we've talked about Laplacian matrices. I'm assuming an understanding of what a spectrum and eigenvalue is, but just know that there are a set of numbers associated with the matrix. Because Fiedler was only working with undirected graphs, like we said earlier, the undirected graph has a symmetric adjacency matrix and a symmetric Laplacian therefore, and a fact of symmetric matrices is that they have all real spectra. So when a random matrix is taken, it can have complex eigenvalues, and in that sense, an ordering doesn't make sense, and to say the second smallest doesn't really make any sense because you can't order the complex numbers. But because Fiedler was only working over real eigenvalues, the smallest is well defined. And you might ask why we take the second smallest instead of the smallest. That's because on a Laplacian, if you recall the definition or you look at your handout, the out degree will always be on the diagonal entry, and then elsewhere in that row, there will be a -1 for every edge in that out degree. So if you have a 3 on your diagonal, you will have a 3 elsewhere, 3 -1s elsewhere in the row. If you have a 7 on your diagonal, you will have 7 -1s elsewhere in your row. So we see that our row sums will be 0. And putting that in linear algebra terminology, the all ones vector, which we're defining as E, will be in the null space. It will be an eigenvector with value 0. So a fact of Laplacians is that they are all singular as well. So since every single graph has E as an eigenvector and 0 as an eigenvalue, it's not that informative. So that's why we move up to the second smallest eigenvalue. So here's another example, as we had before, or this is our example from before, and the spectrum is 0, 0, 2, 4. So 0, again, contained in the spectrum of every single graph. 2 here is going to be our algebraic connectivity, as Fiedler defined it, which is wonderful. And now we're going to move from the undirected case to the directed case in which we can have directed edges. And this is an example to show that contrast. So here, every edge is symmetric. 1 is connected to 2 if and only if 2 is connected to 1. Here, we have an edge from 2 to 1 where we don't have an edge from 1 to 2. Sorry, other way around. But a consequence of this is that our Laplacians are no longer symmetric. So here we have the Laplacian of the undirected cycle, and here we have the Laplacian of the directed cycle. And we can see that this is an asymmetric matrix, which means we are going to have complex eigenvalues, which we cannot order. So this presents a problem because notions of connectivity still clearly apply to directed graphs, perhaps even more so since there are more directed graphs and n vertices than undirected vertices. Obviously, in an intuitive sense, the empty graph with no vertices is less connected to the complete graph, and we can think of there being a spectrum in between those two extremes that we'd like to measure. However, until 2004, there was no definition of alpha, the algebraic connectivity for directed graphs, until Chai-Hua Wu came along and defined it in linear and multilinear algebra. Here's a picture of him. He works at IBM. He's still alive. We've actually been in contact with him about this project, and he's excited to potentially work with us in the future. So this is his definition. He defines a set S. Oh, Jason is jingling his keys. He likes that. First person to jingle some keys. I like it very much. We can go for an audio, but we'll take an emoji in the chat as well. So Wu defines this set S, which is the set of all vectors in Rn perpendicular to E, where E is that all ones vector that have unit length. And he defines alpha as the minimum of this expression, XTLX. And again, this minimum makes sense because X is going to be all real, L is going to be all real. So this inner product will always be real. And one reason that this might make sense as a generalization is that Fiedler excluded the 0 eigenvalue directly by saying we're just not going to consider it. Wu is sort of excluding the 0 eigenvalue by excluding its eigenvector from this set that he's going to consider, XDLX. And this is a true generalization in the sense that if you apply it to a directed graph, it will agree with Fiedler's. Sorry, if you apply it to an undirected graph, it will agree with Fiedler's definition, but it can also give algebraic connectivity values for undirected graphs. This is good progress. This is what we wanted to see. So again, here's our directed Laplacian. Here is the spectrum, which cannot really be ordered. And we have the algebraic connectivity, which is the minimum of this expression, which is 1. So that's wonderful. So here's our work. Just to summarize, Fiedler defines alpha for undirected graphs. Wu defines it for directed graphs using this expression. This expression, however, looks similar to the numerical range. So instead of limiting X to only work over real vectors in Rn, we said, what happens if we allow X to be in the complex set? Well, in the same way that Fiedler only looked at a set, the spectrum, Wu looked at a real line segment, basically, or the minimum of possible real values. We are now looking over a complex convex set. It's a bit of a tongue twister. And we define the restricted numerical range, which is a slight modification you can see on your handout from the regular definition of numerical range, as X star Lx, where S is in this redefined set S, which is really just a complexification of Wu's definition for real vectors. So our motivation from this was to, instead of only look at, again, a real line, to look at an entire convex set. And we do have a useful result that just as Wu's generalization was still accurate on Fiedler's original domain, our generalization is still contains alpha as a value. We have a complex convex set, but alpha, which is Wu's and Fiedler's value, will always be the minimum real part of that set.
Michael, can I ask a quick question?
Sure.
Okay, actually, okay, so yeah, on this page, I guess so when I was reading through your thesis, I was just curious as to how how you came up with your definition of the restricted numerical range, like why you decided, how you knew that this was the right definition.
That's a great question. Yeah, is that
right? But yeah, I mean, I'm guessing that it came from Wu's definition, like, or was there more to it that you had considered before settling on that as a right definition?
So we went directly from Wu's definition to this definition, but the reason it really makes sense is you want to always exclude this E vector the same way that Fiedler wanted to exclude 0 from the spectrum, because excluding the eigenvector associated with that 0 eigenvalue will just remove it. So we have lots of cases where if we look at the unrestricted numerical range, which is just the numerical range of the Laplacian, it's much less interesting, or I suppose less specific in terms of geometry for a lot of, and you'll see this later in the presentation, but there's very specific geometry often associated with the restricted numerical range, because in a sense it's getting more specific information about our graph specifically. Every single graph is going to have E as an eigenvector and 0 as an eigenvalue, and a property of the numerical range is that it always contains the eigenvalues. So whereas others, we might have our entire numerical range, up somewhere in the complex, in the complex plane, having that 0 eigenvalue will sort of stretch it out and lose the information we want. So it did move directly from Wu's definition, but it's motivated by just always excluding this, useless piece of information.
Okay. And was it clear to you from, I mean, maybe clear is not the right word, but did you expect that the restricted numerical range would be capable of characterizing all these classes of graphs that you deal with later on? Like, was that like expected from the beginning, or like was it just like, happy coincidence in a sense?
It was investigatory, as all mathematics was. We were
Okay.
optimistic, but we didn't have any sort of expected results from the get-go, like, oh, this is going to be this and this is going to be that. But as we found more and more specific geometries of the restricted numerical range that we then found were directly associated with certain class of graphs, we gained confidence. And we would periodically check back and say, what does the unrestricted numerical range say about this? And it was always less interesting.
Okay. Yeah, it's just sometimes like when you come up with the definition, sometimes you just have you have reason to believe that something is going to work out. But yeah, I was just curious.
Thanks for the question.
Yeah.
So I mentioned that we now have a complex, I'm going to say it one more time, complex convex set. And here they are. So these are three numerical ranges of matrices. We have a triangle, a vertical line, and a single point at 0, you might notice. Here are some more. This is what I have the file named as a guitar pick. This is a polygon. This is a cone. Also kind of looks like a baseball field if you squint correctly. And then lastly, we have a real line. We have what kind of looks like a 3 ellipse, perhaps. Oh, there's some key shakings. That's great. Love to hear it. And a ellipse. And as I promised, we're going to move on to some characterizations, which are if and only if statements about graphs and their restricted numerical range. So we begin with rather easy stuff. The empty graph, the graph with only vertices and no edges. So here's the empty graph on 1, 2, 3, and 4 vertices. Here are their numerical ranges, which are all in the same X and Y sets. Pretty uninteresting, but also similar for similar structures of graphs on different number of vertices. And here's the theorem we have. Let G be the graph G is the empty graph if and only if the restricted numerical range, L of G, is the singleton 0. That is, G equals En, the empty graph, if and only if, as I said, just in more mathematical notation, the restricted numerical range is the singleton 0. And so, as I promised, these examples hold up. We have all singleton 0 numerical ranges for these empty graphs. That's the first basic characterization. Now we looked at the complete opposite, the complete graph, graphs who have every possible edge. These also have singleton restricted numerical ranges, but you can see it kind of moves to the left. For 2, it's 2. For 3, it's 3. And for 4, it's 4. Just a note, if we were looking at the unrestricted numerical range, to maybe address Jan's question, you'd have an eigenvalue here, and we'd have an ellipse, which is just less interesting because, in fact, all graphs on 3 vertices have ellipses as numerical ranges. And we have a second theorem, the complete graph theorem. For n greater than or equal to 1, G is for n greater than 1, G is the complete graph if and only if the restricted numerical range, L of G, is the singleton n. That is, G equals Kn if and only if the restricted numerical range of L of G equals n. There we go. We got some keys jingling. Good to hear it. Show your Czechoslovakian pride. We're doing the work of Fiedler. And these are just labeled examples of these restricted numerical ranges, 2, 3, and 4. And now we move on to the cycle, the directed cycle. So we have the directed cycle on 4 vertices, which you recall was our first example, as well as on 5 and 6 vertices. And here are the restricted numerical ranges, which is rather interesting. In fact, we noticed that the cycle is a cycle in the restricted numerical range, which was really a mind-blowing moment and one of the things that gave us a lot of confidence in our research. We have a cycle on graphs, which when you transform it into this linear algebra representation and then transform it again into this representation in the complex plane, somehow it comes out the same. Quite amazing. In fact, it will be the convex hull of 1 minus this power of a root of unity for j equal to 1 through n. Fun fact, 0 is missing there precisely because we excluded the 0 value, eigenvalue, by excluding E from our set S that we consider the restricted numerical range over. So, recalling our first 2 theorems, we have a third theorem, the cycle. The graph G is the cycle on n vertices if and only if the restricted numerical range, L of G, is the convex hull of 1 of that power of 1 minus that power of unity, which I'm not going to say. That is, G equals C and n if and only if, that is a typo, the restricted numerical range is not n, but is this set, in fact. Oh, geez, wonderful. Great to hear it. I should get my own set. And aesthetically a little more pleasing. Maybe the one advantage of the unrestricted numerical range is that if you look at the cycle on n vertices, it literally is a cycle on n vertices in the complex plane in the restricted numerical range zone. So this was a great moment of inspiration for us, but I also think it's a learning point for mathematics in general. You can analyze this. You can say, well, normal matrices have restricted numerical ranges or numerical ranges that are the convex hull of its eigenvalues, and the cycle is a circular matrix, and its a spectrum can be described as a linear combination of powers. But I think sometimes it's important to step back. And here's a quote from William James shared with me by Professor Liederman: "The union of mathematics with the poet, fervor with measure, passion with correctness, this is surely the ideal." So we certainly have enough emphasis. Great, a lot of keys for that. We certainly have a lot of emphasis on correctness, but I think we need to take a moment for passion as well. So a minute is a very long time, as one famous band said, but we're just going to take a minute here to reflect on this quote and try and reflect on maybe more aesthetic parts of mathematics that we appreciate, not for their analytical results, but for their aesthetic sublime beauty. So I'll start the stopwatch now. Minute is indeed a long time. That felt like quite a while, but I hope we were able to reflect on the aesthetic and things we enjoy in life in this quote. I also got the chance to breathe, which I appreciate. Thank you.
You did it. You mean who we sent the email to?
Hi, Mom. So we're going to move on to further characterizations. One of the images you may have noticed is that the empty and complete graphs are not the only singletons. So we sometimes have singleton numerical range. Here we have 1, 2, and 3, where this image, a convex set, is just a single point, even when we don't have empty and complete graphs. And this was the first time that we started with noticing an interesting geometry of the numerical range, and then said, I wonder what graph produces this. For the first 3, we said, these are well-known class of digraphs. To just check if our method works, do these have any direct association with the restricted numerical range? So just briefly, we're going to need the directed join, which is a definition that's on your handout. And it's a bit technical, but you can just think if you have a set of vertices H and a set of, or a subgraph V, it's just taking every single edge possible on V and putting it on H. So here and boom, and hence where the name exploding star comes from. So the K imploding star is if you have a center that has a bunch of vertices and then an outside that is an empty graph. In other words, they're not connected to each other, and those ones on the outside are just, all their edges are going into K, which is completely connected. And this is called the K imploding star, which of all the graphs that are named by their geometry, I think it's one of the more apt ones. And so the reason I define these is because we were actually able to first define this class of digraphs. This wasn't well studied. The cycle and the empty and the complete graph, they're known as like very elementary class of digraphs. But we said, well, we had to sort of construct this from scratch. And then we said, okay, these are the types of graph that have singleton numerical range. And here's what they look like. We have 0, the imploding star on 5 vertices onto 1 is this. On 5 vertices onto 2 is this middle image that has singleton numerical range 2. And on 5 vertices exploding onto 3 is this really cool looking matrix graph that is 3 vertices on the outside, 2, 3, and 4, imploding onto 1, 5, and 6. And this was a characterization we were able to come up with. So reviewing our theorems, we have those. I'm going to clear the slide. And now we have this new one, imploding stars. For k greater than equal to 0, G is a k imploding star on n greater than k vertices, if and only if the restricted numerical range L of G is the singleton k. Wonderful. Exactly. Go Czechoslovakia. Go Velvet Republic. Down with the Soviet Union. And we're actually able to further this result. Not only are all, I suppose, integer k restricted numerical range, when you just have an integer like 3, 4, and 5, not only are they always k imploding stars, we were actually able to say that anytime you just have a single point numerical range, it is going to be an integer. And since we know that all integers are imploding stars, we can say all singleton numerical ranges are integers, and so they correspond to k imploding stars, which is a really strong characterization, and we were very happy about. Further, traditional methods of analyzing digraphs or I should say there's an entire field of analyzing graphs and digraphs called spectral analysis, which just looks at the spectrum, the Laplacian matrix, or perhaps the adjacency matrix. And if we look at the spectrum of the one imploding star, it's 0 and 1s, and for comparison, here is our numerical range. This is kind of comparing the new, what we did, the restricted numerical range, with the old, the standard method. And here it is for 2. This is the spectrum, which is 0 and all 2s, and here is our version. They're rather similar, but I'll justify my comparison in a moment. And here is all 3 in the spectrum, and here is a numerical range that is strictly 3. The great, I suppose, success or great triumph of this characterization is that k imploding stars are not characterized by their spectrum. So if you give me a spectrum that's 0 and all 3s, you can't guarantee me that the graph that produced that spectrum is a k imploding star. And as a counterexample, here's a k imploding star drawn a little differently of 6 vertices onto 3. And here's a graph that's almost exactly the same, just this edge that was going from vertex 1 to vertex 4 has been moved from 1 to 3. So they're different graphs. Nevertheless, they have the exact same spectrum. So if you were given the spectrum here, you would not know whether you had this graph or this graph. However, their restricted numerical ranges are different. So this is a moment where we could say our method is actually superior to what's been used before. If you give me these 2 restricted numerical ranges, one of them corresponds to the k imploding star, and one of them doesn't. So moment of great triumph for us here.
Wait, Michael, the multiplicity of 3 seems to be different.
I was wondering if anyone catch that. Very good. Yeah, it is a deficient eigenvalue. It has, I have a note about that just in case anyone asked. It has geometric multiplicity less than its algebraic multiplicity.
Okay, okay. But the spectrum doesn't take into account multiplicity then?
So the spectrum does, if you want to be specific, take into account multiplicity, but a counter argument to saying, I guess it actually is characterizable because the spectrum has different multiplicities. I mean, the spectrum is a multi-set, so you can talk about the multiplicity of entries. Is that when you have deficient eigenvalues, that's a very numerically unstable operation, is finding those eigenvalues. So if we're talking about this in a practical sense, certainly, I mean, the theoretical difference is the multiplicity changes, but in a practical sense, it's not very useful to say, oh, well, you can tell the difference between these 2 graphs by their spectra. Just look at the difference of the geometric multiplicity, because that's a very unstable problem. And if you wanted to apply this to large graphs, which is what most characterizations are useful for, that would be a bad idea because you very easily get round off error. But great catch, very sharp.
I had a just curiosity too. So that, are you saying the ellipse there, the entire colored in ellipse is the restricted range in this one?
Yes, yes, correct. Yeah, so I did mention that normally unrestricted numerical ranges are ellipses. But in this case, the restricted numerical range of that, what we call degenerate K encoding star S star, is an ellipse as well. Or, you know, I mean, hard to see what the second foci is. So maybe just an odd geometric shape, an ellipse-like shape, at least. Yeah, two good questions. Thank you. And so, yeah, that was a great point that we were able to characterize them in ways that they characterize a class of graphs that are not characterizable by previous methods. And in our study of singleton points, we happen to come across points that have a single real value, which makes sense if we're looking for singleton points. I think at first we said, oh, all of these numerical ranges are singletons, and then we said, oh wait, some of them could have imaginary parts, which led to this next class of graphs that have vertical line restricted numerical ranges. This is an example of a graph on 5 vertices that has 4 eigenvalues. It's 5 regular eigenvalues minus the 0 eigenvalue corresponding to E. You can see it lays at 2.5. And this is the vertical line with, I guess, 1, 2, 3, 4, 5, 6. So a graph on 7 vertices that lies at 3.5. And to characterize this graph, I'm offering a definition. This was a previously defined class of graphs. This is the one we sort of discovered through our investigation. A graph G is a tournament graph for any 2 vertices U and G, exactly one of U and V, exactly one of U, V, and V, U, are an E. So definition, the name of this definition comes from the idea of a tournament where each team plays each other exactly once. And a regular tournament, continuing with that analogy, is a tournament in which every team has a even record, an even win-loss record. So every vertex in a regular tournament has the same in degree and out degree. And that is only possible on an odd number of vertices, not possible on even number of vertices to have a regular tournament. Excuse me. And the reason, of course, that I introduced these is we have a characterization for regular tournament digraphs. A regular tournament digraph, we have here the regular tournament on 7 vertices, on 5 vertices all the way to the left, on 7 vertices, and then I've even gone and added the regular tournament on 9 vertices. And they all have vertical line restricted numerical ranges. And we can actually add this to our theorem statements. A graph G on n vertices is a regular tournament if and only if the restricted numerical range is a vertical line with real part n over 2. Wonderful. And just as we could further our definition for integers, all vertical lines are of this form. So if you have a vertical line, it can't be at n over 4 or any other potential expression of n or value. It will be at n over 2 for a graph on n vertices. So all vertical lines correspond to regular tournament graphs and vice versa. Another wonderful characterization we have. Now, naturally, if we talk about vertical lines, we want to also ask about horizontal lines, which we did indeed find in our investigation of new restricted numerical ranges of graphs. So for this characterization, I'm going to introduce the definition of 3 balanced, which should be expression number 4 on your handout if you have that. And a graph is 3 balanced if for any 3 vertices, I, J, and K, we have this expression holding. Now, when I read this, it's not very pleasing to the eyes. My eyes sort of gloss over all those italicized indexing variables. So I'm going to show you examples of 2 3 balanced graphs and state our thesis statement, our theorem statement, which is, of course, that a graph G is 3 balanced if and only if its restricted numerical range lies entirely on the real line. So we also, just as we have characterizations for vertical lines, we have characterizations for real lines. And again, this 3 balanced definition was not something that really existed before. It came out of us figuring exactly what type of graph would have to have a real line restricted numerical range. And this definition is perhaps the least intuitive of all, so I'm going to walk through some examples. So this is a graph which I claim is three balanced, which means for any three vertices, if you take those three vertices, equation, I believe, 4 will hold. So for example, I'm going to take the vertices 1, 2, 3 and the subgraph induced by them, which is a way of saying, fancy way of saying all the edges that are contained in those vertices. And a way that I like to describe three balanced is if you arrange the three vertices as you would on a clock face, the number of edges that you encounter in the clockwise direction is the same as the number of edges that you encounter in the counterclockwise direction. And that number can be any amount. It just has to be the same for any choice of three vertices. So if we're looking for these three vertices and we go in the counterclockwise direction first, we have an edge from 2 to 3. And if we go in the clockwise direction, we have an edge from 1 to 3. And so since the direction is the clockwise sum, say, is the same as the counterclockwise sum is 1, that is an example of those three vertices being three balanced. And we claim that that is true for any of these, or any choice of three vertices in that graph. And I'll just run through an example, maybe a little bit more complicated one on this larger graph. So if we take vertices 2, 3, and 5, and we look at the edges in the counterclockwise direction, we have an edge from 3 to 2. And we also have an edge from 2 to 3 in the clockwise direction, so that's 1 each. And now we have another in the counterclockwise direction from 5 to 3, so that's 2 counterclockwise, 1 clockwise. And there is our other edge in the clockwise direction, so it is three balanced. And so that is the example, and that concludes, I suppose, our full characterizations or our complete characterizations, or at least the work that we have published. Yes, thank you. Very good. Down with the Soviets. Da. Хорошо. And now, just briefly, I'm going to introduce you to our current work. So a class of graphs that we're working on now are those that have polygonal numerical range. You've already seen an example of this, which is the cycle. The cycle will always have polygonal numerical range. And that is by virtue of it being a normal matrix. In fact, we know that all matrices that have normal Laplacians will have normal restricted Laplacians as defined via Q matrices on the handout in expression 3. However, those are not the only graphs which have polygonal restricted numerical range. So the first case of our graphs, which is perhaps the easiest case, are those that have a normal Laplacian and a normal restricted Laplacian. And in that case, we know that a normal Laplacian implies a balanced graph, and a balanced graph is in which every vertex has the same number of edges coming in as edges going out. And we also know so we know that if a matrix is normal, it will have a balanced graph, and it will also have a polygonal numerical range. However, neither of those converses are true. A polygonal numerical range does not imply a normal matrix, and a balanced graph also does not imply a normal matrix. In fact, we believe they're sparse. So we believe that almost all, in the limit sense, balanced graphs are not normal.
Quick question. So is that definition of balance seems not consistent, isn't the same thing as the three balanced from earlier, is it? So
no,
okay, there's
not.
a
Yeah.
couple
So
different...
balance refers to specific vertices. For every choice of one vertex, the in degree and the out degree will be the same. Whereas three balanced is a definition we constructed and has a more nuanced and I suppose less intuitive definition.
Yeah.
But it refers to the group of the three vertices being balanced as opposed to the single vertex being balanced.
Right. So, well, you might watch that, because I think when you talk about the general balanced, it talks about K balanced as well, and that could include three balanced. So you have two different definitions of three balanced. So you'll want to.
So in that definition of K balanced, I meant K balanced in the sense that you could have a four balanced graph where if you took any four vertices, you could have the clockwise sum and the counterclockwise sum being equal.
Yeah. The same.
So I suppose I'm just sort of going off the cuff here, but in that sense, balanced is one balance, where if you take any one vertex, the number of in edges and out edges are the same. But yeah, perhaps we could refine that definition so there's less ambiguity there. So again, our first case, which we have some results for, but no if and only if statements, is if the Laplacian itself is normal, in which case we have polygonal numerical range. Case 2 is in which our Laplacian is not normal, but our restricted Laplacian is normal, as defined on the handout, where instead of looking over the set S directly to restrict our numerical range, we use a class of Q matrices, which we define, which are orthogonal projections onto that space perpendicular to E. So it allows for a matrix representation of the restricted numerical range, which allows us to directly pull a lot of known results on the restricted numerical range, which is a well-studied object in linear algebra. But all that to say, there is a case where the Laplacian is not normal. Nevertheless, the restricted Laplacian is normal, so we can still use properties of normality to somewhat work our way back to the original graph representation given a polygonal numerical range. Nevertheless, there is a third case, which we have found evidence of, in which neither the Laplacian nor the restricted Laplacian are normal. Nevertheless, we have a polygonal numerical range. And I will show you the examples we found of all three cases. So here's an example of case 1. This is a graph that has a normal Laplacian. Here is an example of case 2, which has a normal restricted Laplacian, but does not have a normal Laplacian. And here is case 3, which has neither a normal, Laplacian or normal restricted Laplacian. And the numerical ranges of all three of these digraphs are polygonal. The restricted numerical ranges of case 1 and case 2 are similar. However, those axes are the same across all three of these, so it is shifted, though its geometry is the same. And case 3, what we believe is often happening with case 3 is that one of the properties of the numerical range is that the spectrum has to lie within it. And often polygonal graphs come as the result of, polygonal restricted numerical ranges come as the result of the spectrum being those, polygonal restricted numerical ranges often come as the result of the restricted numerical range being the convex hull of the spectrum. However, eigenvalues can sort of hide in the middle once we get up to a certain number of vertices. So this is one of the first examples we found on it. We have a triangle, which is the convex hull of these three eigenvalues. We have another eigenvalue hiding in the center, which sort of prevents this relationship between the numerical range being the convex hull of its eigenvalues and the matrix being normal from existing. And so we believe that case will be the most challenging to characterize. But that is up to almost present day. Just this morning, Dr. Cameron forwarded me an email from Paul Zachlin, who has worked in translating the original, seminal paper on the numerical range by Kippenhoff. And he has read our paper. He says it might be able to characterize essentially cyclic digraphs, which I don't know what those are because I only read this email at 9:04 this morning, and it was sent at 9:32. But our research is very much active. We hope to do more research this summer and publish again on the characterization of polygonal numerical ranges. And it's an ongoing project. Mathematics lives in the present. And thank you for coming to my work and my presentation. I'd like to give thanks to Dr. Thomas Cameron, my advisor and co-author on our published paper, as well as Dr. Alex Wiedemann, who is my co-advisor and a co-author on my paper. Further, Dr. Heather Smith has been my professor for graph theory and was my second reader. Really helped me take my thesis from, an original draft to somewhere so much better than it is now, and I'm very proud of it. And I appreciate her very detailed work and also a sense of humor. I think she got my joke that I left in the thesis. Further, I'd like to thank Dr. Yang Zhuang and Rich Neidinger, who are committee members and very attentive listeners by their questions, certainly. Dr. Lori Heyer, my major advisor, who's been a constant guiding source and has been great for checking in on me. And Carl Yerger, the chair. And of course, all of you, thank you so much for coming. Thank you for participating. Long live the glorious Czechoslovakian Republic and a non-violent Velvet Revolution. That is all.
Спасибо.
Благодарю.
Hello.
All right, well, Chris, thanks for coming.
Great job, Michael. Wouldn't have missed it. Enjoyed it.
Thank you. Oh, well, I can see everyone here. I couldn't see everyone while I was presenting. We got Dusty, Harry, Miguel, Kevin, Nana. My grandmother is here.
Bill Belichick.
And our dog, Bill Belichick, is here. Is Sarah there?
Wait, hang on.
Great. I have my Aunt Joanne, Dusty, Faith, my parents, wonderful. My high school teacher, Doug Eichmann. We have some Duff guys, Jonathan, Kaylin, all the way from Palestine. Thank you for coming. I have to visit there someday. Brody, my roommate. Katrina, Aunt Kathy, and Uncle Dave. Thank you. Paul, wonderful. Good to see you. Don't ask me too hard a question. We got Tom from Hawaii, Satyajit from India, Calcutta, I believe. Hey, Bruce. Paul, Nora came. Thank you, Nora. Mac, wonderful to see you. Another Duff. Madeline, how are you? Great baby picture. Katrina. Sherwood Ogu, all the way from Turkey. Got a real international crowd here. It's great. Uncle Andrew, Jason,
Kathy?
all the way at Davidson. Kathy's here, yep. And are you out on your porch, Tommy?
I'm in my bedroom with Yuko.
Hi, Yuko.
Hi.
Great view. Are they filming any more Pirates of the Caribbean movies there?
What, Michael?
Any more Pirates of the Caribbean movies being filmed outside your window?
Not right now, but you'll have to come out and see us.
I will.
Hey,
And
Michael, awesome job.
thank you, Tommy. I appreciate it. And lastly, we have Uncle Andrew coming in, Aunt Trisha, Jason, Yara, Nick Johnson, Sanjam, all the way from India, Nir Sato, thanks. Max, my cousin, and Donna Raynone. Uncle Bobby might be here as well. So great to have you all come. I really appreciate the support. It's been a long journey with a lot of work, and it's been fun, and I'm glad that despite the COVID circumstances, this is a bit of a silver lining that I get to have people from all different parts of my life come support me at this culminating moment of my senior year.
Yay, Mike, yay.
So
My keys are too quiet. Not enough metal.
All right, there's your teacher.
So maybe
Hello.
I can move the committee to a breakout room, and then I don't know if we have questions for Michael, but Michael can come back to this main space so that y'all can chat if you'd like while the committee deliberates.
So anyone who can.
People don't have to leave.
Yeah, you don't have to leave. Please remain. I will defend from hopefully not too much of a vicious attack. Hopefully the Czech Republic will hold up. And then after that, I'll be able to come back and share the results of that defense and hopefully just get to hang out.
Where are the refreshments?
I have a beer ready. I don't know about you.
Mm-hmm. You deserve it.
Thank you.
I have a smoothie. Oh, now I can see everybody.
Hi, Jean.
Hey, Jeannie.
Yeah, so you guys will be able to stay in chat, but I'll be moved into a breakout room shortly.
Can you hear us, Michael?
Can we chat
Yes,
with each other?
Sorry. Yes, you can. So you'll be able to stay in chat with each other.
Can you hear Kim and I? Hey, Kim.
I can. Hi, Terry. Hi, Kim. Thanks for coming, you guys.
I understood everything you said.
I expected you to. So.
It was amazing, Michael.
Yeah,
Thank
we
you.
wrote notes, and we're going to use it at some point.
Well, thank you for not asking me too hard of questions in the moment and embarrassing.
Oh, yeah, I got a question.
You can move us pretty soon, Heather, as soon as
Okay.
you want. We need to get the faculty together.
Yep. Okay. Do we need Michael in the room with us?
Yes.
Okay. All right. So I'm going to go ahead and do that, and then Michael can come back.
Okay, bye, Mike.
Bye-bye.
Hi, Michael.
How long will that-
Bye.
How long will that
Michael.
be, Michael?
Good luck.
Let's see. Did it? Wait.
So
I missed somebody.
Jan is not here, I believe.
Yeah, he is.
No, he is.
He's in hand snacks.
Oh my goodness.
I think. Yen, is that you?
Yeah. That's Jen. So we can all unmute. This will be challenging because first we have to. Every honors thesis has a question period where the faculty can ask questions, and then has a faculty deliberation, which will take another configuration of breakout rooms.
Oh, I think, Michael, do you have a leave breakout room button?
I do.
Yeah, I guess that's true. Yeah, that will work fine. Yeah,
So I think you'll be able to go out and we can just stay here.
That's good. All right. So, well, I called for it, so should I start? I've been working hard reading through this, and I'm going to send you a document right after this. I have all kinds of comments scattered all throughout, from little typos to some serious questions and some conjectures and other things. But anyway, so I wanted to. I've got, like I said, a number of questions. Maybe I'll start with just a vague softball that can have a brief, vague answer. It's really cool the way this software plots these numerical ranges, and I'm wondering if you could give me a brief idea how the software works, and then the big picture. Wondering, do you have any geometric conception? I think of the numerical range or restricted numerical ranges as being a transformation of the sphere in C.
Yes, the N ball. Yeah.
Of the sphere in Cn to some set in the plane.
Yeah.
Complex plane. And do you have any geometrical intuition of what that transformation is like? And maybe.
Yeah. So first question, computationally. Yeah, that is a big part of our work that I was potentially going to include in the written thesis that I ended up not because of, I suppose, time constraints, but also this way it sort of does have a very clear theoretical focus. But it was difficult to calculate whether or not a point was a singleton. Certainly, we had NumPy functions from that. What I ended up doing was looking at the variance, and if the variance is below a certain tolerance on all the points, and I can say it's a singular point. The variance is below a certain tolerance, just on the real part, then it's a vertical line, and a similar analogy for complex values and a real line. Calculating whether or not a numerical range, because what we do is we just take, or originally what we did was we just take a 3